Hello, everyone. Well, this is going to be fun. We just launched version 15 of Wolfram Language at Mathematica this afternoon, and I get to play with it with you guys. It's actually, let's see, next week, it will be 38 years since we launched version 1 of Mathematica, what we now call Wolfram Language. And it's been a great ride. We built this huge tower of technology that's let us do lots of kinds of things. And it's exciting in modern times to have realized that things that we developed for a long time, that we kind of did because we thought they were the right thing to do, it's actually turned out that the way the world has developed, it was even more the right thing to do than we knew at the time, particularly in terms of the interaction with modern AI and things like this. I mean, just to kind of set the stage for what we've thought we were doing for the last 40 years or so now, it's a question of how do you formalize the world in computational terms and then get your computer to help you deal with that formalization. So kind of the way I think about it is it's kind of there have been various types of formalization of the world that have been done, whether it's logic, whether it's mathematics. You need kind of a notation for these formalizations. Like in mathematics, there's mathematical notation that got invented maybe 500 years ago or so now. What we've been trying to do with Wolfram Language is invent the kind of computational notation for talking about the world, and not only the notation, but also the way of actually operating with that notation to do computations. I view our language as being a language to think about things in computational terms with. It's kind of a framework for thinking, which happens to be a framework for thinking that is a bridge between the way we humans think about things and the way computers can do things. And that allows us to get sort of the immense power of actual computation applied to the thinking that we do, the kind of computational thinking that we do in Wolfram Language. And we've been on kind of a unique journey of kind of integrating as many things in the world and making them computational as we can directly into the language. It's not like a programming language where you're just implementing particular sort of low-level operations of the computer. We are trying to implement a version of the world, so to speak, in computational terms in our language. And so I view it as being a language to think in, a language to communicate with computers in, but most importantly, a language to formalize the world computationally with. So in modern times of AIs, well, back 17 years ago when we released Wolfram Alpha, we built the capability to go from sort of random natural language to something that was precise and computational. That's a powerful capability, still very useful today. But what's come in more recent years is the ability to have this kind of conversational mechanism with AIs where you're using neural nets to kind of to do things. And the question really is the transport layer for the things that get done with neural nets has been predominantly language, human language, also to some extent programming languages, and now also with Wolfram Language, computational language. But the point is, the LLM is doing what it does, just as things happen inside brains that we don't really understand what they are. But in the end, things get kind of concretized when they're expressed in some kind of language that lets them be kind of transported to other minds and so on. We have natural language, and the question is, how do we, when it comes to AIs, what is the kind of transport layer that we need to deal with things at a sort of precise computational level? And that's kind of a unique niche that Wolfram Language plays. It's kind of the formalization of things in precise computational terms that can be used by humans, by computers, and by AIs. And that's turning out to be a tremendously important thing, whether it's something where the AI is sort of formulating its thoughts in computational terms and then sort of delegating to Wolfram Language to get computations done, get accurate knowledge results and so on. That's one sort of mode of interaction. Another possibility is that it's really something where the AI is producing Wolfram Language code for the human and saying, is this what you want? Is this what you mean? Because when the AI produces Wolfram language code, that's sort of a precise computational formalization of an idea, and that a human gets to say not, oh, are you roughly saying the right thing in words, but is this in fact the computational thing that I intend? And if the answer is yes, you take that piece of Wolfram language code, you use it as this kind of solid brick on which you can build a sort of taller and taller tower of capability. You know, it's been interesting in modern times, everybody's gotten very excited about the idea that you can automate lots of kind of programming with LLMs. And I think to me, that's been like, well, that's not really a surprise because we've been automating programming for the last 40 years or so. That's kind of one of the ideas of Wolfram language, is take those lumps of computational work that people want to do and build functions that just do those things. Make that as automated as possible. Put all the effort into design so that all those components are composable, so that everything fits together in a coherent, unified way, so that you can kind of not just use kind of what was already built, but build your own tower with the capabilities that exist. So for me, I kind of view myself as kind of having lived the AI dream for decades now, as I kind of make use of all of that automation to do the kinds of science and things that it's my hobby to do. And it's been quite remarkable sort of how far it's been possible to go by using kind of the leverage of the automation that exists in Wolfram language, both in terms of practical automation and, as I mentioned before, in terms of using the language as kind of a way to formalize one's thoughts computationally. But so kind of we've known that you can kind of automate things, and users of Wolfram language have been doing that automation for decades, and it's been a very direct path from kind of you have an idea to you can implement it in Wolfram language and see what its consequences are. That's something that at the very beginning of Mathematica 38 years ago, for many kinds of mathematicians, scientists, and so on, there was kind of a dramatic moment where you could go from, oh, I have to get some programmer to write code to do this, to with my own fingers, I can get Mathematica to do the things I want. And you can make sort of a tight loop where you take the idea that you had, see its consequences, go back, come up with the next idea, and so on. And in all these years, that's been something we've seen happen in sort of leaders in science, technology, in companies, CEOs, CTOs of companies, making use of our technology to kind of quickly go from an idea to an actualization of that idea. People who've been kind of in the trenches doing programming with standard programming languages, that's not the model of their work. The model of their work is not come up with an idea, actualize the idea as quickly as possible, go on to the next idea, and so on. Their model of work has been much more, I'm given a spec for what I should code, and then I kind of grind along making that code for weeks or months or whatever, and then I come back and I ask for another spec. Well, that's the thing that got automated. It's no surprise that that was automatable. We've known that was automatable. That's what we've done for the kind of computation that Wolfram language does. But it's interesting to see that. It's interesting to see that what you want from the LLMs, from the AIs, is you want that thing that is the kind of computational artifact that comes out of creating that code. And so another dynamic that's happened in recent times is, which is kind of cool to see, is that a lot of people like product managers and people who think about products and so on can go from the idea they have to, oh yeah, let's get a website that does those things. They can do that with an AI. And so long as the website more or less looks right, all is good. What the code looks like underneath, nobody cares. So long as it basically looks right and kind of does the right thing, it's all good. However, there are many things in the world where it actually matters knowing what you're computing. It matters what the actual computation underneath is. And that's true in many technical areas, in areas of science, engineering, education, and so on. You need to know what you are computing. And so then the question is, well, how do you know what you're computing? Well, you have to have some representation of the thing you're computing that you can actually read and understand. And that's not thousands of lines of, I don't know, Python code or Java code or something like this. But what we've done with Wolfram language is to make a language which is intended to, as succinctly as possible, communicate computational ideas. It's sort of the whole idea of our computational language is to have something which is not just writable by humans as a thing to throw at their computers to execute, but as well a thing that humans can think in terms of. And that's something that's incredibly valuable. And that's something that now there's a source for those kind of valuable artifacts of Wolfram language code that isn't humans writing it, it's AIs writing it, showing it to humans, saying, is this what you mean? Is this what you intended to compute? When you use Wolfram language in that way, you're doing computations where you know what you are computing. And that's kind of a big, that's sort of an important piece of the picture in terms of what one can do with AI at this point. You can, as I say, if all you need to do is say, does it look right? You know, did I generate a picture of a fire-breathing dragon that looks like a fire-breathing dragon? Okay, yes. It doesn't matter what the pixels are exactly, so long as it roughly looks like a fire-breathing dragon. On the other hand, if for many activities, it's important to actually know what you're computing. If you're going to push it in directions that you didn't already foresee, if you actually want to make sure you get the right answer, if you want to be able to build on top of what you have in a way that is sort of a way where you have a kind of a solid thing to build on, in all those cases, you need to know what you're computing. And that's where our computational language is critical and unique. So the thing that we kind of embarked on, well, more than 40 years ago now, of building this computational language to formalize computational thinking about the world, turns out that was a really good idea. And it turns out that's a good idea, not just for humans, but also for AIs. So that's kind of a picture of where we've got to. And I would say that the kind of the automation that we've done, kind of AI is sort of another kind of automation. We make some use of it. It's helpful to us, although probably not as helpful to most software companies, because we've already automated so much of our development process. We've already kind of recursed on the development that we're doing. We build capabilities and then we build on top of those capabilities. And we've been building that tower for the last 4 decades or so. So that's kind of where we're at now. As we've built that tower of capability, it's been a very satisfying activity, because the things that we did in version 1, well, they're still with us today in version 15. And in fact, we've been able to maintain basically perfect compatibility between version 1 and version 15. It takes a lot of effort and I think foresight to do that. And over the course of 40 years, it's possible, 38 years now, 40 years since we started developing this technology stack, but 38 years since it's been available to people to use, that you can take something that was built for version 1 and run it in version 15. Well, so we've been building this kind of stack of technology, and the thing that's happened is we've got a bunch of kind of design methodologies and kind of ways to think about making things computational. And as we build this tower taller and taller, it's been very interesting to see to what extent we can see further. We can see other things that can be made computational. It's something where we build a certain kind of conceptual framework, and then we use that framework to build more further conceptual frameworks and so on. And so we'll see in the course of development of Wolfram language, various kinds of frameworks that emerge, whether it's the entity framework, whether it's the user interface framework, all these kinds of frameworks that once they've emerged and they're really well designed, then you can build on them for decades to come, and you kind of get more and more power from having more and more frameworks. And so we'll see in version 15 a few new frameworks that are arriving, but we'll also see a lot of development from existing frameworks, a very powerful functionality that was kind of seeded by a framework that we might have developed 10 years ago or so now, but now that kind of comes to fruition in the things that we're able to do in version 15. So it's a very impressive release. It's got a lot in it. The 14.x releases, 14.0, 14.1, 14.2, 14.3 have also been impressive, but the jump from 14.3 to 15.0 is particularly impressive. And well, let me get going and show you some things. All right. So you can read about the things that I'll be yakking about here in the post that I made earlier today. You can see there are lots of sections here that we get to talk about. So let's start off with, we were talking about AI. Let's start off with kind of the question of how we make use of AI in Wolfram language. So one of the big new things is that when you open a Wolfram language notebook now, you will see, I'm going to show this as a slide because we can't magnify it on the screen to show you a different way. At the bottom of your notebook, you'll see a box that says, what would you like to do? That's a connection to an AI. And it's something we sort of pioneered with our notebook assistant more than a year ago now, year and a half ago now. And this is now kind of mainstreamed as a thing where you can say, well, you know, do something for me, solve something, it will generate Wolfram language code. The way it works is you type into this chat bar at the bottom of the screen, and it'll pop these cells that are chat cells. You can work with those chat cells just as you work with any other kind of cell. You can, for example, close up that cell group so you only show the input to the chat, not all the things the LLM responded. You can delete cells, you can move them around. It's a very convenient way to work with a chat and with notebooks. We kind of pioneered that mechanism 3 years ago now. Now it's really mainstreamed in every notebook. When you use the chat bar, there's kind of a default AI set of capabilities that you get. That's part of our CAG, Computational Augmented Generation system. That's what's going on under the hood. For sort of basic, hey, how do I roughly do this? The default chat bar is going to do everything you want. And it's kind of the not just, hey, tell me what's in the documentation, but also put together pieces of code and so on, sort of small things. If you want to really do all of your work sort of in Wolfram environment with the sort of fanciest AI you can get, well then click the button and sign up for the higher levels of AI capability, Pro and Research. Research gets you to the sort of best frontier models. Pro gets you to something where you can really be having serious long conversations with your heart-to-heart conversations or something with your AI. And by the way, for those, if you don't like the chat bar, you press the X and it'll minimize itself. I thought I was going to do that, but the UX that we have for the chat bar and the way it's kind of a translucent thing at the bottom of your notebook means I don't switch the chat bar off. And whenever I need to use it, it's right there. It's a zero-click experience. Okay, so that's a little bit about using AI from inside Wolfram language and Wolfram notebooks. By the way, I should say that we've had for ever since 2023, we've had the ability to programmatically make use of LLMs with the LLM function and other functions like that. And that's now plugged into this whole system that you get with the AI assistant. Okay, well, so that's thing number one is kind of you're operating in a Wolfram notebook. You want to make use of some AI, have a conversation with the AI a bit. There's another case, which is what if you're using kind of an outside AI system, ChatGPT, Claude Code, Cursor, I don't know what, some other system. And you want that system to be able to have access to Wolfram capabilities. Well, now that's possible. There are two big things that we are releasing here. Let me show you how this works. So the basic idea, this is a little complicated. So it's a little, the flow is a little complicated. Let's see here. What I want to show you is, well, okay, you can find some of this from our front page. In fact, you know, our front page used to be just for humans. Now it's for AIs as well. If you press the For AIs button there, you know, if you're doing that as a human, well, you're kind of pressing the wrong thing, but you can do that. And this is a markdown page that kind of tells you as an AI what you should be doing and takes you to the right places. But let me show you at a more human level what we're doing here. So there are really two components to this technology. One is remote MCP server. That's one piece. And the other is a local MCP server. And I think there's a page where we explain both of them. Let's see, here it is. Okay, so what is this? This is the way that the AIs can connect to Wolfram language. And this is where the AI is doing the connecting. The AI is sort of in charge. What I talked about before was Wolfram language is in charge, Wolfram notebooks are on top, and you're calling the AI. This is the AI calling Wolfram technology. So two mechanisms. One is the cloud MCP mechanism, where the AI is running and it's calling out to our cloud servers to get computations done to access Wolfram technology. That's thing number one. And thing number two is you're running a local AI app, which is itself using a remote LLM, could be a local LLM, but mostly it'll be a remote LLM. But it's accessing a Wolfram engine that's right on your computer. So if you have your own Wolfram 1, Mathematica, whatever, on your computer, you can have your AI make use of that on your computer with access to being able to read files or whatever else on your computer. You can get access to that through the local MCP system. Okay, so let me explain that again. So let's say you're using ChatGPT or something. You want to have ChatGPT be able to do Wolfram language computations, and you want that, and you just want to call that whenever the AI feels like doing it. Well, what we released today is kind of a Wolfram Alpha-like thing for LLMs. Wolfram Alpha is kind of your one-shot, drive-by, convenient way of getting access to sort of the power of Wolfram language and our technology and knowledge base and so on. It's a one-shot thing. You type an input, you get an output, you're done, you go on to the next thing. And it's a free capability on the web that's existed now for 17 years. What we're doing as of today is to make a similar technology available for LLMs. It's the Wolfram Cloud MCP system, which is kind of a one-shot, if you're an LLM, you can go ask it something and you'll get a result. Actually, the Cloud MCP system uses both Wolfram Alpha and also Wolfram language. It can both take a query from the LLM using natural language or using Wolfram language. And there's a whole bunch of additional technology in our MCP server that provides extra information that's part of our computational method generation system that provides extra information to the LLM to guide it to make the best use of Wolfram language and so on. So as of right now, you can just go to ChatGPT or Claude or any of a whole collection of other AI systems, and you can just go to settings and click the button that says enable the Cloud MCP, Wolfram Cloud MCP. I think this might be one of them. Is this it? Oh, what am I looking at here? This is, okay, I just opened, well, okay, here, let's look. This is in ChatGPT, you can just go to the apps section and you'll find the Wolfram app and you just press the connect button and it is then enabled in your ChatGPT. Okay, for the local MCP system, the way you enable things is kind of from, well, you can do it in a variety of ways, but let me just show you. I want to show you what, oh gosh, that's the wrong thing, sorry. Okay, this is for Claude. This is the page for the MCP server that allows you to connect to Claude here. But what you can do, we've made it sort of very convenient to be able to make those connections, and you can do it from within our technology. So for example, when you launch Wolfram language, when you launch Wolfram Notebook system, in the welcome screen, at the top of the welcome screen, there'll be a blue bar that just says configure your, and it will look around for the different systems, AI systems that might be installed on your computer, configure your Claude Code, Codex, whatever else, to use your Wolfram system. Then when you go there, you click that, and it will show you the various environments. So this is in the preferences dialog. It'll show you the various environments that you can configure to use the Wolfram local MCP server. Press configure all, and it'll all just work. And once you've done that, you can go into Claude Code or something, and you can say, go run this in Wolfram language. It'll go do it. It'll call the evaluator tool. It'll go and do that computation, bring the results back. The thing that comes back is an MCP app that can have sort of rich content. If it brings back code, it's click to copy. So you click the code, you can paste that into a notebook, for example. It's a well-integrated thing. It works. I found it super useful. I mean, to be fair, LLMs do get confused from time to time, and they'll sometimes be like, oh, I can't really find that evaluator tool. You just like tell it, go look harder, and eventually say, oh yes, I found it. It's a bit confusing. I think it's one of these things where when companies very proudly say they wrote all their code with AI, and then you look at what their code actually does, and they're like, oh, wait a minute, somebody should have looked at this. This doesn't really work very well. The UX doesn't really make sense. It'll all get worked out. But what we've built is sort of the standardized connectors to make all this plumbing work. Okay, so that's a bit of the story of making use of our technology from within AI environments. All right. Well, one of the things we haven't in this version, kind of the AI story is a story, but it's not by no means the only story. There's a huge amount of new core functionality in version 15, and I want to tell you about some of it. So where do we start? Well, let's talk about time series. Something very useful. Actually, I'm going to make one more comment, which is another thing you can do if you want to if you want to use AI tools from within Wolfram language. I showed you how you can do that from the welcome screen, but there's also a function, deploy agent tools, that will deploy, that will set up all of the things on your computer system necessary to have agents make use of Wolfram language through MCP and so on. So you can just run that function, or you can use the welcome screen, or you can use the preferences dialog, all of those different ways of doing things. I should show you one more thing, which is just as you can use the chat bar at the bottom of the screen to be able to inject kind of AI content. So also where you can use what you've been able to do for a long time, which is type a single quote, and that gives you a chat bar, a chat cell anywhere in your notebook, and you can start typing here and talking to the LLM. You can also press this button here. This UX is slightly different than the way it was previously. You can press that button, and a sidebar will be extruded that allows you to have kind of a side discussion with the LLM This is kind of it's sometimes convenient to do this where you don't want to kind of muddy up the nice notebook you're looking at and you really want to see what's going on in the notebook and you have a side conversation here. Sometimes you want the conversation you're having to actually be in the notebook, and that's where you use chat bar and chat cells and so on. Okay, so having said that, let's, I'm always rather allergic to doing AI-based demos, so I'm not going to in real time start asking it things. I'm just going to use reliable computation to do that. So we were talking about time series. We've had time series for more than a decade in Wolfram language, but in version 15, they're dramatically extended, enhanced, and so on. What's made that possible is the tabular framework. So here I'm going to import a fairly big time series. Let's bring that in. This is a time series with 13,000 entries. Came right in. Now we can let's kind of preview that time series. We can press the preview button here. We'll see a preview of that time series here, this is all, that particular time series has many columns in it. So it's making use of the fact that it is underneath time series are now tabular objects. Tabular objects are objects that have columnar data in them, and we can do that. So in fact, if you want to see the tabular for your time series, just say tabular of the time series, there is the tabular with its various columns here. One of those columns, one of the keys for the columns is the timestamp. Okay, so what can you do with this? Well, you can do all the things with this that you're now able to do with tabular. So I talked about how frameworks build on each other. This is now using all the mechanisms that we introduced for the tabular framework, like the ability to take to plot things where you're just saying extract that column from the tabular and plot that. We're now doing that with this time series. We're saying geolist plot that time series, this particular column in that time series. So we can also say, let's say, for example, here we can say let's plot another aspect of the time of it. Let's say here we're plotting the elevation column in this time series, and now it's plotted against time in this plot here. Let's say we want to do a computation on this. We could say let's take the moving average of the time series, the 15-minute moving average of the time series, and plot the elevation component of that. Okay, well, so we also, from this whole time series mechanism, this is in a sense not just a tabular, because we can ask, it's not just a tabular with sort of fixed rows for the different timestamps. It's a time series which is sort of beyond a tabular because it's interpolating the time elements. So here I'm asking for an interpolated elevation at this very specific time here. For example, we can use all of the kind of granular date mechanisms. So this is a time that is granular to an hour. And so this will now average the elevation over that hour in the time series. It's using the granular nature of the times to say we want the elevation, but we want it for that whole hour, not for an instantaneous piece. So just like with tabular, we also now have a time series summary, which gives us kind of a convenient visual summary of what's in our time series here. Okay, well, let's see, we can look at, I think I had another example here in the post. I'm not sure I can use it here. This is going to be a boring fake thing because I'm just going to show the image of it. We could take a data bin. I didn't have this prepped. We can take a data bin of my heart rate data for the last 9 years or so. And this is a data bin that's been being accumulated in our data drop system for the last 9 years. and I could just say time series of that data bin. I will get a modern time series. This all happens quite snappily, and you can start doing computations on it. Okay, that's a bit on time series. What is a time series, really? A time series is something where there are samples of some process at a particular sequence of time steps. But what you imagine in a time series is that something interpolates between those time series. So if this was my heart rate, for example, and we have data every, I don't know, 5 seconds about my heart rate, then we guess that in the seconds in between those 5 seconds, my heart rate will smoothly interpolate between the values that it was at those two endpoints. That's kind of the nature of what we expect in a time series. Now, in Wolfram language, for a dozen years or more, we've had both time series, which interpolate data, and event series that correspond to just point events. Like there was an earthquake then. I pressed this key then. There's no sort of continuous, what are the keys in between the keys I pressed? It's just there are events that happen, discrete events that happen. So just as we've updated time series, we've also updated event series. And so what we can do here, well, this is actually going from a time series to an event series. So what this is doing is it's saying, let's sample in the time series, in the continuous time series, we want the every 10-minute local maxima of this elevation data, and that will give us an event series. So in this particular case, that event series, we can say normal of that event series. I think it just has 5 different events there. But in general, we could have extracted, we could have filtered out of a time series an event series. And so we could go ahead and plot those along. We plot both the time series and the event series. So now we'll be seeing the time series with those events that were the local maxima, the 10-minute local maxima plotted on it. Okay. So we can do, there are a bunch of new things. There's another function called event series lookup, which will go ahead and figure out for example, in this case, it's a particular granular date. It'll figure out what events are within that date range. So it's a way of kind of, again, filtering events in an event series. Okay, so that's the news on time series and event series. I think this is super useful. There are tons of applications of this. Time series, event series are now incredibly efficient. You can have a time series or an event series where every time step or every event has many columns of data associated with it. That's a very convenient thing for many applications, whether it's in finance or in all sorts of other areas. Okay, so that's something on time series and event series. Our next topic, categorical data. So sometimes there's numbers associated with data, but sometimes there's just a category, small, medium, large. Okay, in version 15, we're introducing kind of a new symbolic representation for categorical data. And the point is that categorical data, this is an ordinal which can be small, medium, or large. And so, for example, we can get the particular ordinal that represents small out of this collection of ordinals, small, medium, large. Well, now we can do things like we can say, okay, we've got this ordinal object that is an ordinal, small, medium, or large, and this is categorical data that's ordered, ordinal. There's also categorical data that is not ordinal, which is a pure category, but we'll look at that in a minute. For nominal data, like, I don't know, dead or alive or something, where it's where there's a well, actually that's a bad example. Let's say male and female as nominal data, where there isn't a definite ordering to them. It's not like, you know, male comes before female or something like that, as opposed to small, medium, large, where there's a definite ordering to that. Okay, so once we have any kind of categorical data, we can, for example, make random choices. So here we're making a random choice out of the ordinals small, medium, and large, and we're getting that collection of things there. And these icons, they're kind of cool little icons because they show you those little, if you can see, I'll make this bigger, 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 bigger. Oh, those pieces don't magnify, huh? Maybe if I magnify the whole notebook, it will magnify. I'm going to try that. Okay, just for a moment, we're going to go to 300%. And yes, they do magnify then. And you see these little dots here. Well, the dots are meaning medium is the middle one of our ordinals here. And so it gets little dots there that indicates that in its icon. Okay, let's go back to a more civilized size. All right. So one of the things we can, with ordinals, we can do all kinds of things. Like we can say, what was the maximum of that collection of things? And because they're ordered, it says the maximum is large. We can also make a categorical histogram. So a new kind of histogram where instead of it being numerical values, it's these categorical values. Since these are ordered categorical values, ordinal values, it puts them in that sequence. Okay. So there's a whole mechanism of categorical distributions. So we can make a probability distribution over these categories. So this is a categorical distribution over those ordinals. And now we can start doing, this is where, all these frameworks fit together. This is what's really cool. If we say the probability that X is a small, where X is distributed according to this categorical distribution, we can just evaluate that. And it's going to say this categorical distribution, which is just these unweighted three categorical values, we say, what's the probability to get one of those values? Oh, it's 1/3. Okay. Well, sometimes you can just, there are scores that you can get. We can assign a score where we do say small, medium, large is 1, 2, 3, for example, and we get that. Okay, let's talk about nominal data. So nominal data doesn't have this notion of ordering. So this is now nominal data, ABC nominal data. Again, if we say what's the max of that, it's going to say it doesn't know. It's I guess it had no A's in it. So it's the max of B and C because these are just sort of undefined symbolic nominal categorical objects. So you can't resolve the max in that case. Okay, so this notion of categorical data, it can appear in time series. It appears in probability distributions. It's getting integrated into all aspects of the system, this notion of categorical values for things. All right, so along the same lines, where we're talking about sort of data and so on, big new thing in version 15, the model fit superfunction. So we've had the ability to fit data in all sorts of ways in Wolfram language for a long time. This is a very powerful new approach that really ties into Tabular and machine learning and lots of other kinds of things. So we have the notion of a symbolic model. So this is an exponential model. It has no particular parameters associated with it. The variables parameters are blank. But now we can say, make a model fit to an exponential model of that data. And now we'll take that data and it will say, okay, we're going to make an exponential model that fits that data. And here's that best fit to that model. And now we could take that exponential model and we could say, let's evaluate the exponential model at the position 5.6. And this is a univariate model, but we could do this with all sorts of multivariate things as well. So this is basically saying, I've got this data, I'm making this fit, and now I'm going to use that fit. As I say, we've had lots of capabilities for fitting in the past. There's just a much cleaner way of setting this all up. And for example, what we could do here is we can say, okay, we're going to make a list plot of that data with plot fit being that exponential model, and then it will plot it in that way. Actually, we could have the fit done. This is something that was actually added in 14.3. We can have the fit sort of done automatically within the very plotting function. List plot can take a plot fit option that is just an unfilled in exponential model. It just says fit some kind of exponential model, and as you're doing that plotting, fill in the fit and use the correct the best fit exponential model. Well, we can ask all kinds of questions about that model. We can say, how good is the fit? For that, we can ask for a report on the model fit. And there's our report with all kinds of residuals. We can go and drill in and ask for parameter estimates and so on. We'll get all kinds of data about the parameters for the fit and confidence intervals and so on. We can kind of drill it all the way down. We could also say, we can also talk about models where we've named the parameters in the model, we could, when we're doing that, we could say, okay, we've got a general model, but we're going to say A is 0. So we just say 0 UV. And now we can go and use that model with the, well, this is with ABC. Okay, so now we're asking for parameter estimates directly from that data. We can get all of that. Well, there are all kinds of models we can use, exponentials and logs and power laws and all kinds of things. Let's do one example of that. Let's say we have data on exoplanets. So we're going to fit a power law model to the semi-major axis and the orbit period of all the exoplanets that are known. We have those exoplanets in our knowledge base. We're going to fit a power law model to this. Notice that we can already see the fit is R to the power 1.47. Well, those of you who know physics and astronomy will know that's Kepler's third law, that the orbit is proportional to the 3/2 power of the semi-major axis. So we just were able to, with one function model fit here and our knowledge base, we were able to sort of, well, we got a lot more about this than Kepler had. We were able to, I'm now curious, of course, how many, for Kepler it was, what was it? It was probably 7 planets or something. But now for us, it's, let's see, I can just say the length of the entity list of all those exoplanets. I wonder how big that is. Okay, we got a lot more, so we should get a better fit. And indeed, we discovered this law of physics, which then got explained by Newton's law of gravitation, et cetera, et cetera, et cetera. And let me not digress onto science. But anyway, we can ask, for example, to take our model here and predict based on an orbital a distance from our star of 1 astronomical unit, predict from the model how long that orbit should take, how long it should take to go around that orbit. And the answer is basically 1 year. So we verified that for the Earth, this actually works based on this fitted model. Okay, well, we can actually fit, we can take data and we can, in this case, we are fitting to any polynomial with degree up to 5. And we're trying to find the best fit model based on various fitting criteria for this data based on a polynomial where we allow powers up to 5, but in this case we didn't choose to use it. We can see why didn't we choose to use it. Let's look at the fitting report. If we drill this down, we can look at model selection and we can see, okay, this was candidate model 3 of 5, and we can see that was degree 3, degree 4, degree 5, and it decided it didn't really get much by using a higher degree. So actually we could, if we wanted to, okay, we can get the cross-validation chart for this, and if we wanted to, we can actually take the original data and just show our fit, do our whole fit, polynomial model fit up to degree 5, right inside our plotting function, and plot that fit as well there. Okay, so for example, the linear model very convenient kind of model. It lets you specify any linear combination of a particular set of terms. We can also have formula model, which lets you specify a model in terms of an arbitrary formula here. There are lots of kinds of models that we have, and more will be coming in future versions. Here's another one. This is, we've got a model fit where we're fitting to a periodic model with, I guess this is two possible periods that fits the periodic model. And in general, with these models, there can be many sort of hyperparameters in the models, and we can specify all kinds of aspects of that. We could say here, oh, here we're fitting, what's this? This is fitting a time series. Okay, maybe that was the same time series. But we can specify hyperparameters about the fit. That is, we can say in this periodic model, we're saying we want this count of number of frequencies, this number of sample points, and so on. And now, when we do that, we will get fits with those values of the hyperparameters. Okay, well, we can sort of generalize not just traditional statistics style models, but kind of more machine learning oriented ones. And so here's an example of one of those. So now we're just making a nearest model. So this is saying we've got our data points, and I want the nearest neighbor with these bins of size 1 to my data. Okay, and so that was with single nearest neighbors. I could go ahead and do third nearest neighbor fits, and this is now fitting based on what's the value that's third nearest neighbor. Oh, actually here, this is just kind of a Voronoi-like thing where just saying what's the nearest neighbor to this and what is its value. Here it's what's the third nearest neighbor. And all of this stuff can be done with great generality, as is typical in the things we build in Wolfram language. So this is a 3D version of a nearest model, nearest neighbor model compared to data. Okay, so this particular data happened to come from a tabular, and like we can with other functions, model fit can extract columns in a tabular just with this rule syntax here. So now it's extracting from the Fisher iris data, it's extracting those three things. It makes a nearest model there. And we could then say, okay, let's get list plot 3D. Oh, okay, this is a different model now. So now this is, I think that's the same data. This is a multi-layer perceptron, and now it'll actually have to do machine learning type training to find the perceptron model, to find the appropriate perceptron model, which optimizes the fit. Now we can go ahead and do that, and eventually it will come back. And this was now a perceptron model fit to that data. And by the way, if we wanted to, we could find the actual underlying network there. Oh gosh, it's going to have to compute it again. I should have just extracted it from that nearest model, but anyway, never mind. This will compute it again, and now there is the actual machine learning net chain with all of its detail underneath it. That was the thing that got learnt from this model fit. Really very nice way to access, kind of to bridge between kind of statistics thinking and machine learning thinking. Well, we could go ahead and in here, we could have changed the hyperparameters and the perceptron. We could go and give it a different depth, different width, and so on, do all those kinds of things. Okay, another type of model, let's let it do its thing here. Another type of, an issue here is, okay, we get this perceptron, this neural net out. We don't really know what the neural net means. We want an interpretable model. Okay, well, how do we get that? Well, one of the types of data that gives you a more interpretable model is a decision tree model. So this is taking the classic Titanic data set and asking it to make a depth 2 decision tree model. And this is now, so now we can kind of see if sex is male, if age is less than or equal to 13, true, false, et cetera, et cetera, et cetera. That's making a decision tree for, I think, oh yes, there we go. We can see some more of that. given that decision tree, oh yes, we can do this. We can just say, given the decision tree that we just created here, we can now say, okay, given these categorical, these actual inputs, class first, age 90, etc., what will be the prediction for, what will be the survive prediction for that piece of data using the decision tree model? Okay, very kind of, I think this is a very easy to use version of decision trees and so on. You want to see the tree, you can just say tree of it. Now you're plugged into our tree framework and you can do all the things that you can do with trees and all the kinds of computations with trees. Okay, so that was the story of model fit. Very important superfunction. I expect to be using it a lot. You know, we've had a variety of kind of more junior versions of fit, find fit, and so on. But this is really dealing with symbolic models in generality in a way that plugs into machine learning, plugs into probabilities, plugs into tabular data, plugs into time series. It's all integrated, and this is new in version 15. All right, so that's a little bit on that. Let me let's go on to something completely different. In the history of kind of formalization of things, something that was very related to the formalization of mathematics was music. And the idea that there was a certain amount of formalization you could do about music. You could have notes and chords and harmonies and octaves and who knows what else. Well, in our effort to sort of formalize, computationally formalize everything in the world, we finally got to music. We've had capabilities for music in Wolfram Alpha for a long time. We finally have gotten them to the level where we think they're general enough to be part of Wolfram language. It's kind of a hierarchy for us of things where we put them into Wolfram Alpha for kind of one-shot computation. We get them to a higher level to get them into Wolfram language for really systematic computation. So, music. All right, here's a musical pitch, A sharp. Okay, it's just an A sharp there. But if we say, okay, what's musical pitch? B flat plus A sharp minus C. So A sharp minus C is a musical interval, and plus B flat gives us a new value here. And of course, there are lots of subtleties in music, like is C sharp the same as D flat? Yes, it is. That's just the way it works. Well, now, so kind of the lowest level thing in our kind of symbolic music mechanism is musical pitches. That's the pitch of a note. Now we can actually define a note. A note is a pitch. I could have put musical pitch in here. It's a pitch for a certain duration. And then we start to see it here with a stave, and it has a little, oh gosh, I think I didn't connect this. That's no fun, is it? Let me see if I can do that. That was a mistake. Let me see. How can I do that? I wonder if I can do it. Let me see what I can do here. If I say this and I try and do this again, trying to figure this out. Let's try this. And let me that. And with luck, when I mouse over this and press the play button, oh, what's happening? Well, okay, it did work. I think it got a little bit confused by the chain of ways that I'm showing things. Did you guys hear that? Yeah. Okay. So let's talk about, well, so we've got this note here, this musical note. We can always say what's the pitch of that note? Okay, we'll get out a musical pitch. And we could ask what's the duration of that note and so on. And you can certainly do arithmetic on musical durations. So, okay, so we have this notion of a music duration. So remember that a music duration, it's not it's not something, it's a certain number of beats that we're dealing with for a particular note. Okay, so beyond single notes, we also have the notion of chords. So here's G major chord, here it is. And we could say, for example, of that, what's the pitch list in the G major chord? And there's the answer. And we could say, then we could say, what are the intervals that exist there? So we're doing all kinds of computations. So now the musical intervals are these major thirds and so on. Let's see, we can also do something like algorithmically construct an interval. So we do a nest list here where we're progressively adding a minor third starting at C, and we're doing it 4 times. And that will generate this chord with many notes in it. We could go ahead and take that chord and we could say, add the musical interval, add music interval 5 semitones to that musical chord, and we get another result. And probably if I, yeah, a little bit ugly, but we can play that chord if we want to there. Okay, so there are other things like music rests and so on, but then there are measures, musical measures here. Let me try something here. Something has gone strange with my... Oh, that's why the thing got confused earlier when I was first trying to play this sound. For some reason, it had connected but frozen the camera. All right. Let's see. All right, so this is a music measure, a series of music notes. There they are displayed. We can play them. Okay. It's by default, it's assumed to be in 4/4 time. We could specify a different time signature here, 3/4 time, for example. Then, okay, what's the next sort of level up in the music hierarchy? We have a musical voice, which is a combination of these pieces. We can then we can combine those musical voices together into a full musical score. There's our musical score, 3 measures, we can press it. Okay. So now we've got symbolic music defined. Okay, what about some actual music? Well, why don't we just go ahead and get some music? Here's some resource data, a Bach fugue. Here's the fugue. And this fugue is now represented symbolically as this piece of music. And we can show that in more detail. We can say make a music plot of that. And this will show kind of, I hope, all of the notes in that fugue. It's kind of interesting to see. And of course, we can, if we go back to this music object here, like videos, like audio, we can play this music object here. I guess we can just start it playing, and then we can stop it. I think we can start it anywhere. Okay. Well, we could now do computations on this fugue. So for example, how long does it last? Okay, 32 measures. What's its range of pitches, for example, kind of the min and max of that plot. Okay, C2 to C6. And now let's say, for example, for each voice, let's just make the music measurements on this fugue. So we're figuring out for each voice here, we're figuring out the distribution of pitches used by that voice. So for example, we could do all kinds of things here. We could do, this shows the relative occurrences of different pitch classes in that piece of music. And we can do other kinds of computations. Like for example, here we can try and figure out what key is this fugue in, C minor it says, based on the distribution of notes that are used. Well, if we want to, we can always take this symbolic representation of music, and if we wanted to, we could just take a music measure and we could just say, actually make that into audio, turn that into an actual waveform based on synthesizing those notes and show it as an audio plot or compute with it as a piece of audio. So we've got this kind of hierarchy from symbolically specified music to the kind of symbolically specified music is kind of like vector graphics, and then we've got kind of the bitmap, which is kind of raw audio. Now, we've had capabilities to deal with sounds and sound notes and so on for a long time, actually, for 30 years, more than 30 years. What's new here is really a knowledge of, in a sense, what Pythagoras knew, the mathematics of music, the sort of formal symbolic computation with music. All right, moving along. Let's talk about Tabular. Let's talk about connectivity for Tabular. This is something that we've added capabilities for dealing with very large things like CSV files very efficiently. We can now extract particular columns in those CSV files. We are also in a position to deal with remote data. So we have this notion of data connection objects. So this is a data connection object, which is kind of as if it's a file, but really this is a Databricks data connection object. I don't know if I can actually run this here. That has a bunch of SQL in it. But as far as Wolfram language is concerned, this data connection object, which I doubt I can actually explicitly run right now, this data connection object, we can treat it just like a file, we can import from it, and so on. Another thing that's important is the connection of Tabular to external evaluate, so that we can link together tabular data workflows that include both Wolfram language and external languages. So here's an example of something where we are taking, I think this will work. We are running a piece of Python code in I mean, the fact that this works, it's such a mess dealing with all of these not nicely packaged systems. And okay, what this did, it dealt with the pandas dependency of the external Python interpreter, and it dealt with all of that. And in the end, it had a pandas data frame. But the end result is it's a tabular in Wolfram language, and you can do all the good things you can do with tabulars in Wolfram language. You can export it in other ways, but this is basically a story of how you can go from external data sources and they're kind of messy to get to, but then they just become these kind of spigots from which you can get kind of the data for Tabular. Okay, more about what we can do with Tabular. So took us a long time to develop the whole design framework for Tabular. Let's get a Tabular in here, and let me show you some of the new things that that we can do in version 15. I mentioned, I showed you actually with time series. I showed you time series summary. There's also tabular summary. There's the tabular we just imported. By the way, it's pretty big. This tabular, and it all came in very efficiently, and we could compute the summary. We could, if you wanted to, we could specialize that summary. By the way, the thing that's nice here, this data not saved, save now. It's selling as 1.7 megabytes. You could save this in the notebook. There, it's now saved in the notebook. So now that data will be available the next time I run this notebook. Otherwise, it's just in the kernel, and the kernel is where the data resides. And then you're kind of pulling that out in the front end to look at it. So here I asked for a tabular summary of the numbers on a statistical basis, and this is the result we get. Okay, well, what if we want to model this data? Well, it's really easy. We just use model fit. Now we've got that tabular, we've got these two columns in the tabular, we say we want a quadratic fit, there it is. And this is, I think, probably the trunk size of trees or something like that. Okay, here's another new thing with Tabular. This is entity augment columns. So in this tabular, we had a bunch of, this is a data set of trees, and one of the columns is the Latin name for that type of tree. Well, what we can do is use our knowledge base to augment the data in this tabular by saying, take the species column and add to the genus and order which we get from our knowledge base for the interpreted species that are in that. And so we run this, it'll add to, it might take it a while because it's a really huge data set. There we go. Okay, this expression exceeds the maximum size for notebook embedding, so we'd have to save it somewhere else. And it will give us an option to save it in different places. Okay, so what this did was it went from the species that was here, and it added at the end here, it added two new columns, genus and order, for those species. So this is a way, if you've got data and you want to do an analysis on that data, and you can knit in our knowledge base into your data to enhance your data for analysis by just automatically augmenting the data by new columns using the things that we know from entities. There are lots of other things we've added to Tabular, geoposition columns, geoprojections, around, numbers with errors, all kinds of things like this. All right, let's move on though. Let's talk about visualization. Oh, actually, yeah, here's another thing with Tabular. This is arounds in Tabular. So, sorry, that's being able to have numbers with errors, handling those in tabulars in a very efficient way. Okay, visualization. All right, let me actually bring up version 14.3. And here's, I hope. This is, let me just make this bigger. That's a version 14.3 notebook. And now let me put, oops, that was the version 14.3 mechanism. I am going to render a pie chart in version 14.3. Okay, there's a pie chart in version 14.3. Let's take the same pie chart and render it in version 15. Okay, we brightened the colors. This is part of, colors change. There's trends in colors, and we have a very energetic design department. And one of the things we like to do is to update colors, just like one might do for clothes or anything else. We update colors for modern times, and so we've done that in version 15. That's for that. We could do, let's say, here's a histogram. That's version 14 there. Let's take the same thing in version 15, and hopefully it's a little bit zingier. The yellow is a little zingier. Things, the borders are a little bit quieter, and so on. Lots of things that we've just sort of spruced up in this kind of way. So, for example, here's a what's this? This is a oh no, this is something different. Well, this is okay. This is something different, which actually reveals something, because I'm running here in 14.3 and it's telling me plot style is not an option to bar chart. Okay, well, and one of the things we've done is we've kind of normalized, we've made coherent the way that things work for what we've traditionally thought of as charts, and the way that things work with what's traditionally thought of as plots. And so here we are saying we've got this bar chart, and we're saying we just want to plot this with purple, orange, cyan. Now, the reason we didn't do this before is that it's quite tricky, because the way that we have multiple data sets and things in our typical charts is different from the way we have it in plots. So here we've got these two different sub-data sets, which are in standard green and standard yellow. Remember, in the previous version, we introduced this idea of not just pure green, RGB 010, but a nice standard green. which probably will evolve as the years go by. If you use standard green, your pictures will always look nice and spiffy. Okay, well, the issue, there's lots of things about whether you're specifying individual bars within a group or whether you're specifying groups. That's all been untangled, and it works very nicely in version 15. Actually, we've got a lot of detail. We've got kind of the ability to really dive in and specify things in a lot of detail. So here we're saying we can make plot style, and this is true with many visualization options. They now have an association form. So in this case, we're saying the elements here are standard green, yellow, blue, but then the groups, these groups here, the edge form for the first group is dashed, the edge form for the second group is thick red. So that's the way that we kind of dive in and get detailed control over all the elements and all the pieces of these plots. So you can do the same thing here. What's this? We can do this where we have all kinds of different labels of, we're labeling different, we're doing the same kind of thing we did with plot style here. We're doing with plot labels. We're labeling the groups, north and south, and the elements, zebra, rhino, lion. And that's how that works. And you can now have complete control over those kinds of things. We can use the same idea in list plot. So we now have detailed control in list plot for the plot style, for example. We're saying the base is absolute point size 5. And then in these different lists of data, we're having standard blue, purple, red. So we can now plot style doesn't just become a thing that relates to these different groups. It allows you to set different components of the plot style separately with that association. Okay. Lots of different options and so on. Distribution chart, we kind of modernized this to, by default, make distributions like this. You can use distribution chart has a variety of styles, like you can make a histogram, or you can make you know, the sort of violin style here. You can also, this is just new capabilities for distribution chart. You can make one where you're just showing the density of values going up in these different bins. Okay, other new visualizations, bubble histogram, combination of histograms and bubble charts. This is showing intensity in size and color here. You can control how each of those works. For something completely different, here's another kind of plot we can now make. This is a periodic table plot. So the generic periodic table is just a periodic table here. But if we wanted to, we can plot values on the periodic table. So for example, one thing we could do is plot the property phase in the periodic table, and it'll show us that shows gas, solid, liquid, and no phase at all for the elements that live only a short time. And that's so we can do all kinds of plots on a periodic table. Okay, another important thing in visualization is multi-panel visualization. So this is something I've wanted forever, and we finally now have this working nicely. Okay, let's say I make a bunch of plots. Here they are, a list of plots. But I want to put these together. I want to share the axes. I want to do all those kinds of things. If I just put them in a grid, I'll just get all those original plots put together like this. There won't be consistency between the scales of these plots. Okay, here's a new thing. It's called plot grid, and it lets you take those plots, that list of plots, and make them so that we've maximally combined the axes here. So instead of duplicating the axes for every different plot, we've now combined the axes and lined everything up. Okay, so there are many options for how this works. So for example, we can say this one, we'll notice that the two rows here have different y-axes. But if we wanted to, we can make a plot grid where everything is consistent, where we're saying make it consistent across everything. So now the scale for this top one got extended, and the scales are completely consistent for everything. It can also share labels. So for example, here, I'm giving it some labels. I've told it to do that. I'm sharing the labels. It's maximally shared across these different pieces. Okay, so I think a very important new feature is this plot grid mechanism. It's kind of an outside-in mechanism for combining plots. Just as graphics grid, graphics row are very convenient for combining graphics, plot grid is a very convenient way to combine plots, taking account of the scales that they have and so on. We have other mechanisms to go from within a plot and spawn another plot. That's sort of inside to out. But what we now are providing, which I think is going to be most of the time the most convenient way to do it, is an outside-in mechanism. You've got the plots, now you want to combine them. Okay, the next thing to talk about. Let's talk about things about notebooks. All right, notebooks can be bigger than they ever were before, and they can be gigabyte sized, and that's been a sort of a huge piece of internal re-engineering to make that possible. We built a technology stack when megabytes originally, 38 years ago, megabytes were big. Nowadays, gigabytes are small, and we can now deal with multi-gigabyte notebooks. So in lots of ways. And so, for example, another big thing that's been added is Notebook Find, a new interface for Notebook Find. That's very, if I go here and I say find where I mentioned grid, it'll say there are 4 occurrences. I'm sorry, I think this is small here and I'm not sure I have slides for this. I probably don't. Well, here, let me maybe show you in the actual blog. This is what it looks like. There's a new little interface that you get with Command F at the top of the notebook. It's a very nice, modern, spiffy interface, and it's a find replace interface. You can put all sorts of things into it. You can search for all sorts of elaborate typeset things, graphics, whatever you want. So convenient, easy, and a new thing in version 15. Okay, next topic: visual themes in notebooks. Okay, so the question is, what we have our notebook, and it has, we put a section heading in here. It's in a particular color. There's kind of a theme we can define, which is, for example, accent color 1 would be those colors, and there are 2 of them because we have to deal with dark mode. So, for example, that's accent color 1, and we can see that's in the current theme that we're using. This is what accent color 1 will be like. I guess if I evaluate this, I get, or accent color 4, that's what that accent color is like. Well, okay, what if I want to change the theming of my notebook? Well, I can go to the preferences panel here. Let's see, I go to this. What am I going to? No, not that. Okay, this has to do with the notebook sidebar. So when I press the chat button, that's the sidebar I get. When I press the gear button, I instead get a different sidebar. Oops, here we go, which tells me about the notebook. So for example, I can flip the notebook to dark mode, and I can go and say, this is the theme. So it's a little small, I'm sorry. This is the theme. It's the Wolfram default theme. I could pick. These are now many other themes. So let me pick the Stargazer theme. So that's convenient if you're out looking at your telescope. This is the garden theme. I don't quite know what that is. I guess it's green. The bright theme, and I could flip this back into light mode. But the basic point is, this is a way of retheming your notebook. You just open the side panel here and pick a theme, and pick a theme, and these themes are available in both light mode and dark mode. So it's kind of the evolution of things like style sheets goes towards this idea of themes, and this is how they're set up. The way that it works sort of at a programmatic level is that we're defining these things like theme colors. So within a theme, there will be, if I flip themes here, if I go to, you'll see these theme colors will change as I flip themes. So that was the garden theme, so it all went green and brown, I suppose, for these accent colors. And that's, so we'll go back to the default, there it is. So that's sort of the mechanism for these. Now, you can make use of these accent colors in, so if you have let's say we've got this plot, and we say, I want this plot to fit in with the theme of my notebook. Okay, great. Then use theme colors, not raw colors, not things like standard red or something, but theme color accent 1. And now I go to garden mode, and those colors will automatically change. So this is a way of flowing kind of notebook consistent colors into visualizations that you make. This whole mechanism has meant that, oh boy, this is a funky thing. Okay, so standard red, I can go to this, and now I have kind of a new set of, where are they? A new set of named colors that I'm dealing with here. Oh, here we go. Yes, if I pull down this, I'll see something that says theme color. So now when I'm picking colors here, I can go and pick colors from my theme. So for example, with the standard red, I could pick some purple color that's the syntax 1 color. Oops, I didn't actually choose it there. But anyway, I could have picked the syntax 1 color and connected that to my theme. And then when I change the theme, that color will change. Okay, that was a bit on themes. Let's go on here. And let me show you something else. This is something which I've been using. Oh boy, I've got, shall I leave it in this theme? Nah, let's go back to the standard theme. Let's say I have a really long cell here. Okay, but I don't want to show the whole cell. Well, something I've been doing and things I've written for years actually now is using capabilities to make a torn appearance. So this now has, the right-click menu now has an item that says Allied with Tear. And there it is. We've now got a torn off appearance, and I can move that tear if I want to. But then in this notebook, and it's something where the data is still there, it's just for visual display in this notebook, it has a torn off appearance. And needless to say, it's, you know, the things that can be torn can be, you know, anything. You could have a manipulate here, you can have anything you want here. It's just a visual tear. It's just kind of a shade, a window shade that's showing you only part of it. And of course, it's tricky because as you, if I rerun this particular cell and I say thing of 100, the tear will look the same. And even though it's kind of a random tear, and yes, it uses cell UUIDs and random processes to generate a realistic paper tear and all those kinds of cool things that is kind of almost free for us to do because we have, you know, we happen to have everything for dealing with random processes and UUIDs and so on built into the system, so we can leverage that in this case. Okay, another topic. Let's talk about, we make a bar chart. Okay, and we say, what would that bar chart look like in dark mode? Well, now there's a function, dark mode pane, that will just show us that thing in dark mode. It's a simulated dark mode that we can use to display things in dark mode. So if you're including this in some external document, you could say frame margins to 20, you can just, and the document is dark mode, you can make it a dark mode thing. When I export it as graphics, it will do that, and so on. And dark mode pane is a typical pane. It has wrapping widths and so on. So you can just be sort of as if it's in dark mode and such like. Right. Okay, let's move to something different. Let's talk about the one argument form of monitor. So you're running a computation for a really long time, since version 6. That's, what is that, 25 years more? You've been able to monitor a computation, specifically monitor a computation. So for example, here I could say, monitor the variable n in the evaluation of this table, and we'll see that counting up, monitoring the value of n. Okay, what's new in this version is you don't have to say what to monitor. So for example, I could just say monitor this map. There's no variable there. Well, actually, I did have a name variable here, but there's no visible variable. But nevertheless, I can run this, and it's going to say processing element. Oh, it was cached now, so it was too fast. But and for example, with these tables, I could say compute this table and just say monitor it. I'm not telling you what variable to monitor, just monitor it. And now it's going to unroll the table, and it's going to say processing element 250 out of 300, and it's going to estimate the running time and so on. So this is a convenient thing. You can wrap monitor around some function. It works with specific functions like map and table and lots of others. You can map monitor around things to see that monitoring without having to sort of expose a variable that you monitor. Okay, another thing. This is now sort of in the weeds, but it's very important in practice. It's a framework kind of thing. Subvalues can be held. So here's an assignment for F. We're saying let's make an assignment for G. We can now do we're assigning a subvalue for G. So we're saying if I say G of 7, that's not a thing yet, but G of 7 of 5 uses that value to compute 12. Well, subvalues are very convenient for lots of purposes. We use them all over the system. If you say something like append X, that the one argument form of append has a subvalue. The subvalue of that just does the appending. Okay, well, the issue is that functions that hold their arguments, so a set, for example, is hold first, which means that when you say x equals 3, even if x previously had value 4, the x doesn't get evaluated to 4. It's held so that the evaluation can be done on the raw x, not on the value of x. Okay, well, let's have a symbol u. We say set attributes to hold first. Okay, if we do that, we'll get that first argument of u is held there, doesn't evaluate. Now the question is, well, what is the interaction between holding and subvalues? So let's say we hold all the values here. Now we compute that, they're all held, but we compute this, and this 1 plus 1 is evaluated to 2. Even though the things directly inside the u are held, the subvalue position is not held. Okay, this has been something where it sort of limited some aspects of our design. to not be able to hold subvalues. So new in version 15 is subvalues hold all. And this will take it so that if we say v of 1 plus 1, 1 plus 1, like that, the v of 2, that 1 plus 1 will evaluate, but in the subvalue position, it won't evaluate. And if we say this is holding all the subvalues. And that's something that's important for lots of kinds of operations, whether it's, and this now opens up a bunch of design possibilities to make operator forms of functions and things that we couldn't do before, and for people who write their own functions to make operator forms of those functions. And I think I need to clear these so I don't get messed up later. Okay, another topic down in the bowels of the system, ready to use incremental data structures. So in version 14.3, we introduced the incremental object construct. That is, no, I'm sorry, we introduced incremental function. Incremental function is something where you are repeatedly calling a function and it's compiled and it operates incrementally on a data structure. Now we have the idea of incremental objects. So this is an incremental object. It represents the permutations of 20 elements. So there are lots of those. There are 20 factorial. That's too many to store. But this incremental object is a symbolic representation of those permutations. And if we say to that incremental object, next value of it, okay, there's our first permutation. Let's run next value again. We'll get another permutation. We'll get something here where the 19 and 20 have been swapped. Run it again. Okay, we've swapped again. Run again. We've swapped it again. Again, again, again. We will get sort of successive parts of that whole 20 factorial number of permutations. This incremental object, we're able to sample next values from the incremental object. But now, this is sort of an important piece of this. We can say, let's say we want to make a new incremental object, which is the selection in this incremental object of permutations where the permutation order is equal to 20. Okay, so this is now going to give us, there's now going to be a filtered version of all those 20 factorial permutations, but it's filtered to be ones where their order is 20. And so now we'll have a permutation here, and this will be the next permutation that has those characteristics. And so we filtered it in this symbolic kind of lazy way where we didn't actually do the filtering, but we made a thing which represents the filtering. Okay, and we can check that, yeah, this has permutation order 20, and that was what we were asking for. Okay. By the way, in case you're wondering how many permutations had to be tested to find that one that had that permutation order, the answer was 46,000 in this case. And that all happened when we tried to instantiate this kind of lazy select here. Okay. So permutations we can do sort of lazily now, where we're not actually computing the permutations, we're just making an incremental object that represents them. Same story with subsets. We've got the first 20 primes, and we're saying we want all combinations, all subsets of the 20 primes, where their total is 500, and now we want to say, well, select with that and get the next value of that. That's all the subsets of the primes that have that, and presumably I could say next value. Oh, I didn't store what the incremental object was, but if I had done that, I could keep extracting the next value from the symbolically represented incremental object. There are a bunch of functions for which there are now incremental forms. So what's this? This is an incremental object searching for perfect numbers. And if I then instantiate this, I'll get a bunch of perfect numbers. It's just looking at range of 10 to the 15 and instantiating with that. Okay. Well, let's say I wanted to go on and do and compute another perfect number. Well, actually, I can just pick up this incremental object and I could run it on a different computer. It's just stored in the notebook. The lazy object that is not fully instantiated, just says symbolically what to do, is stored right in the notebook, and I can keep on and keep going with that computation. I can do next value many more times. Okay, let's turn to another topic. Boy, there's a lot to talk about here. Exceptions and error handling. So what happens if something goes wrong in a program? Well, kind of, you can just say return, you can return things, you can use throw and catch, you can throw a value and catch it outside. We've had throw and catch since version 1, 38 years ago. In version 3, and that's 30 years ago, we introduced tags for throw and catch. And then 6 years ago, we introduced confirm and enclose, confirm by and enclose by, confirm quiet, all those kinds of things. They kind of don't affect the operation of code, but they control the propagation of errors that develop inside the code. Okay, so those are convenient ways to sort of locally control errors and to control the flow of errors. But let's say one has a large code base in which there are errors that occur deep inside the code base where you don't want to propagate those errors. You don't want the functions in the code base to have to know about the error. You just want to throw an exception and let something else deal with it. Well, in version 15, we've now built a system for throwing exceptions. So this is, let's define a factorial fact function which throws an exception if x is greater than 69. Okay, so here, now we can define a function that uses the factorial function. And now if we say, let's define another function that catches exceptions, the overflow exception from these functions g. And so now when we use f of 20, no exceptions will occur, we'll just get a result. If we use f of 80, well, there'll be an exception in the underlying function, fac, that propagates into the g function that is then caught in the f function and returns as a failure. If we hadn't put catch exceptions, we just kept propagating that exception up and up and up. Okay, so let's say we can ask for the, no, that's not what we want to do. We want to say, let's compute, okay, so this is f of 20, f of 80, but now let's do that for g of 20, g of 80. So that didn't have a catch exceptions. And there it says, okay, g of 80 generated an uncaught exception. So this whole thing is bad. The g of 20, even though g of 20 would have been okay, the whole expression couldn't get evaluated because there was an exception. We threw the exception, it returned in this case to top level and said, oops, there's an exception there. Okay, so given an exception like that, we can always say what's the exception data associated with that exception, and it tells us about the various tags and so on. Now we can say, let's say that we say catch exceptions of an overflow exception of this g of 80 thing. So we're now explicitly catching the exceptions, and we're saying for an overflow exception, produce this result, this row of overflow exception there. Okay, we can define sort of explicit payloads for exceptions. We can throw explicit exceptions. We can do all kinds of other things. We can define hierarchies of exceptions, lots of kinds of things with exceptions, important for kind of making large-scale code bases. Let me not go through more of that right now here. Let me remember to clear those things. Okay, also in the direction of large-scale code bases, a new thing in version 15 is the structured package format. So ever since version 1.0, Wolfram language packages have been able to have functions like begin package and so on that localize contexts, that localize symbols. We now have kind of a new mechanism for all of this. I think I have to show you this here. This is, yeah, I think this is one of these, come to the webinars that are being done about these things. I'm not going to go into this in too much detail, but the idea is to have packages where things are born private. Usually when you have a package and the things in it, when you evaluate them, they are evaluated in your sort of ambient global kernel. But in this case, in the case of our new structured package format, that's not how it works. Instead, you have symbols which are born private. If you want to export them, you say package exported of those symbols, then you define them and so on. You can also share packages across share symbols across packages. Okay, how does it work? Well, in the structured package format, you put a bunch of files in a directory, and at the top of that directory, you have one file, init.wl, which contains a package initialize, which is normally the name both of your base context for the package and the name of your top level directory. And this all sort of interoperates with the whole packlet mechanism. Okay, so then once you have that in the structured package format, you call needs with a context name, and once you've got that directory tree and it's on your context path, and you have put that package initialize into the init.wl, as soon as you say needs, it will load that package, and it will automatically export, localize, etc., all those symbols. So there's other mechanisms here to do with package import, which is for importing things from another package within a package and so on. But the basic point is there's now a better way to kind of structure large code bases in Wolfram language that has a very powerful way of defining public symbols, kind of shared symbols, and so on across different files. Okay, now for something completely different. Let's talk about something we've done for graphs. This is plotting over graphs. So, oh, actually, that's a different thing. Wait a minute. Well, I think let's talk about okay. Let's talk about plotting over graphs. Okay, this is a new function, graph value plot. So what this does is it says we've got a random graph, and we're going to make the values of the vertices in that random graph be numbers from 1 to 20, and this is now plotting those values with size and color. And so, for example, we could say if we wanted to just use vertex size, then they'll be the same color, and that'll do that. And we could do something like plot with both vertex shape and vertex size, and there we've got results there. We can also go ahead and we can also deal with not the nodes of a graph, but the edges of a graph. So here we're saying, well, we're using the edge betweenness centrality, and we're using that to annotate the edges. So lots of things of that kind. So now another new thing with graphs, tag nest graph. So nest graph is a way of applying functions to create a graph and combine the nodes where necessary. Tag nest graph now tags the different the different elements here with different colors. So if we've got two functions, it will use different colors for the edges that correspond to those two different functions. So here's a slightly larger example. We've got a tag nest graph where the 2 hash is the blue and the hash plus 1 is the orange, and that makes that picture. So another thing in I think I managed to repeat something, and that's what I get for having too much stuff. And I think this is repeated somewhere else. But another thing that's new in version 15 is some new graph highlighting mechanisms. This is the halo graph highlight that just puts a halo. You can put shadows and things like this around things. So let's see. Another thing in version 15 is for low-level graph rendering, vertex shape function. It's always been hard to remember what the parameters for a vertex shape function are. They now can be named, so you can say use coordinates, use vertex in a vertex shape function to determine how you are shaping the vertices in a graph. Okay, another topic. Let's talk about how do you put ticks on a map of the Earth. So here's a rendering of the Earth in a funky projection. But now, what can you do to put axes on this picture? So that's one set of axes, the kind of raw axes in the projected space. But this is another set of axes, the geo axes. This is the regular axes. Now these are the geo axes, which are now axes sort of set up to be on the surface of the Earth. So the equator and a meridian there. Things get very funky. You can put grid lines on that. Here we can do that. I don't know, we can, I think it gets, I don't know, I think I was having fun here. Let's try and do this on a really funky projection. Let's see what's happening here. It's computing for a while here. Oh, there we go. Finally, we've got grid lines with multiple copies of the equator, all kinds of wild things now available. Lots of math needed to make all that stuff work. Okay, and needless to say, because it's all very general, you can put this funky projection on the moon as well. Okay. This particular projection uses Jacobi elliptic functions as part of its math. Well, for these geoaxes, you can, lots of options, you can decide where to put them, et cetera, et cetera, et cetera. Okay, let's talk geography and projections and so on. Let's talk about solar eclipses. Well, we've had some capabilities for these. We've extended these. Let's find solar eclipse. When will the next solar eclipse occur at Stonehenge? 2393, apparently. We could ask in the past, when was there a solar eclipse at Stonehenge? So we say time direction -1. The answer is 1847. I'm sure people had a fun time in 1847. That must have been the time. Actually, now that I think about it, I wonder whether my friend, in quotes, Ada Lovelace, she could easily have gone to see that at that time. Anyway, I have to go look up that correspondence. Okay, so for the 1847 eclipse, what was its path? There's its path across the world. And we can ask now things like, when did that reach Stonehenge? And the answer was 7:25 in the morning, GMT. And we can ask, how long did it last there? All these kinds of questions we can compute 4.5 minutes. That's quite a long eclipse. Okay, actually we could plot a timeline plot of all the eclipses at Stonehenge over the last 10,000 years. There's the result. And if we wanted to, we could plot all of their paths. There's lots of computation needed for something like this, but it'll grind away. And there are all the eclipses. There are the paths of all the eclipses in the last 10,000 years that went through Stonehenge. Okay, another new thing, find solar eclipse for a whole country. So 2044 apparently is the next time there'll be an eclipse visible from all countries. We could now say, okay, let's do a parallel computation here. Let's say find a solar eclipse in all countries. Just find when's the next solar eclipse, and we're selecting which countries have a solar eclipse in the next year. And what's going to happen? Oh, it ran. I have a 200 cores actually in my particular setup. There's the answer for where there will be solar eclipses in the next year. Okay, talking of things astronomical, we're going into orbit, so to speak. Well, there have been copies of Wolfram Language and Mathematica in orbit a number of times. I don't know if there's one there right now. There might be, but this is something different. This is the orbital elements for the planet Mars, for example. Now we can take those orbital elements and make an orbit time series. Now that we have time series really up to snuff, we can go from orbits to time series. So now, for example, we can get orbital elements for Mars 10,000 years in the future. We're predicting now, we're running an ephemeris computation. Okay, we've got to download this ephemeris. And that's now going to give us the predicted orbital elements for Mars 10,000 years in the future. If we take these orbital elements, we can compute lots of kinds of things from those orbital elements. So for example, we could say, get orbit lines for the moons of Jupiter. So you see there the inner moons and the outer moons, which we've now computed from the orbital elements of those moons of Jupiter. We can do the same kind of thing for satellites orbiting the Earth. Now we're going to get the orbital elements for the GPS satellites and see those, see the orbits for those around the Earth. We can do this both for elliptic orbits that are bound and keep orbiting the same body. We can also do it for hyperbolic orbits like Voyager 2, which has escaped the solar system. It's on a hyperbolic orbit. We can go ahead and actually compute the, let's see, this is now computing the distance. What is this? This is the monthly difference in distances for actual Voyager 2. And now we can take the current orbital elements of Voyager 2 and we can compute based on the current orbital elements. That is, after all the burns it's done, after all it's now in inertial motion out in the galaxy, so to speak. And this is showing that it did a bunch of burns as it was probably going through the solar system here, and that changed its orbital elements, it changed its trajectory. Now it's on this sort of free hyperbolic orbit that's just going inertially out into and that's what we get. So actually, we could even, if we wanted to, we can even say what are the orbital energies, and we'll actually see these burns as the thing changes its kinetic energy, I guess, plus potential energy. No, I think it's changing its kinetic energy in as it fires its rockets and so on. Okay, let's dive back into some math. This is about algebras. So in version 14.3, we introduced non-commutative computer algebra, and now we're introducing specific kinds of non-commutative algebras. This is Grassmann algebras, and this is, we can now say, do non-commutative expand on y wedge x in the Grassmann algebra of y and x. Grassmann algebra is non-commutative, is anti-symmetric, so y wedge x is minus x wedge y according to Grassmann algebra. And now we could do the same kind of thing with Clifford algebra. So here's a Clifford algebra with those elements. It's got certain multiplication, certain addition, and now we could say, let's do a non-commutative expand of those Clifford algebra, in that Clifford algebra, x times, in effect, x, and that's the result. We can make something a bit more elaborate. We can do a non-commutative expand in a Weyl algebra. of this slightly more complicated expression, there we get the result. So this is important for all kinds of computations in all kinds of fields. Well, that's a pun in a sense, in all kinds of fields of human endeavor, but in all kinds of algebras here. So we can define our own algebra if we want to. This is an algebra where there are certain generators and certain relations, and now we can do non-commutative expand with respect to that algebra. So we define those relations, and with those relations, this expression can be expanded out to something like this. And there's actually a whole monograph we've created about non-commutative algebras that talks about these kinds of things. So check it out. Okay, more math. Relevant for, well, things I used to do a lot of and might be doing again, things like Feynman diagram computations in quantum field theory. So we've had zeta functions forever. We can take the sum from I equals 1 to infinity of 1 over I cubed at zeta of 3. But multivariate sums we've also been able to do for a while. This is a multivariate sum that can be done in terms of ordinary zetas. But now, here's a more complicated multivariate sum. This is a sum where I to the 5th j cubed, that sum cannot be done in terms of ordinary zetas. It has to be done in terms of a new thing that we call multiple zeta. And needless to say, things, as is often the case, things get pretty complicated pretty quickly. Here's a 3-variable sum, and there it is, computed in terms of multiple zetas. And if that was a multi-loop Feynman diagram in quantum field theory, you'd be able to zip out the answer right there in terms of multiple zetas. And you know, if we do this in traditional form, it at least looks pretty nice and compact with our multiple zetas there. I have to say, I'm back in the day, what kind of got me into doing big algebraic computations on computers back in the mid-1970s was computing Feynman diagrams in quantum field theory, which have a habit of needing very complicated algebraic things worked out. One of the big mysteries to me at the time was a lot of times you did these very complicated computations, but when you added them all up, the result was actually quite simple, which kind of made one think, as my friend Dick Feynman used to say, that Feynman diagrams are not the right way to compute things, but it's the only way we had. And actually in my efforts in fundamental physics, we are kind of on the, looks like we're homing in on what's sort of underneath Feynman diagrams of quantum field theory, but that is a completely different topic, which I should not get distracted into here. So back to the practicalities. And I hope we'll get to the point of being able to actually use these things for sub-quantum field theory at some point. But there's another example of a trivariate multiple zeta, complicated stuff. And even univariate sums with harmonic numbers can involve multiple zetas, and so on. So, okay, zetas are sort of the generalization of zetas when there's not just a 1 in the denominator is polylogs, another favorite kind of function of mine from back in the day. We are now dealing with what we call multiple polylogs, which are these multivariate sums of this type. Now, whenever we introduce kind of a new class of functions, what makes it really difficult is they get knitted together throughout the system. So here's an integral that can be done in terms of an ordinary kind of polylog. Here's an integral that, oh, that's an ordinary polylog integral. But now let's try and do an integral like this. This is a kind of integral that might be, these might be Feynman parameters in a Feynman integral. And there, that comes out in terms of this new kind of polylog, this so-called generalized polylog here. And we've got other integrals that introduce other exotic functions. And the thing that's sort of interesting is that these kinds of functions seem to be kind of what we need to use to parameterize the kinds of things that happen in things like Feynman diagrams and quantum field theory. They seem to be kind of a mathematical packaging of what's happening sort of at the physics layer in these kinds of places. Okay. Again, this is sort of an asymptotic desolve of a differential equation. Let's see what happens here. Well, here we get to use harmonic polylogs as part of the computation of the asymptotic behavior of this particular differential equation. So again, knitting all these functions right into the system. Okay, something more elementary, partial fractions. We have a new function that computes partial fractions in a way that is, if we have the function apart, it will compute something like this, but now the partial fractions are sort of more careful version of a part, where it will really go all the way down. So in a part, we're still leaving these kind of unresolved denominators, but partial fractions, the new function partial fractions, really goes all the way to linear terms there in the denominators. We can tell it to insist on reals, and it'll then go kind of it'll then always make use of reals, and in some cases not able to get to linear terms there. And for detailed sort of computer algebra things, we've got partial fraction elements, which break down how partial fractions work in more detail. Okay, another area, new matrix decompositions. We've got things like LDL decomposition. That's not getting rid of cholesterol. That's breaking a matrix into lower diagonal and diagonal parts. And it's now set up in a convenient way where we're not packing those pieces together. We're having them as separate kind of structured matrix objects. And we can, so lots of things along those lines. LU decomposition now produces these structured matrices. These are just conveniences in working with matrices. We have functions like LU decomposition have existed since version 1, but now we get to package them nicely with these structured matrix objects, which represent matrices in a much more efficient way. New decompositions like rank decomposition, and from which the original matrix can be reconstructed. Let's see, how do we do this? We apply dot to that and we'll get the original matrix, because this is that kind of decomposition. So a whole variety of new matrix decompositions, really covering the waterfront of matrix decompositions. Okay, one thing I might mention on the math side, some things where we're starting to really get benefit from using modern AI in some of what we're doing. And here's an example that I'm going to go to version 14.3 here, and I'm going to try and solve a differential equation. Let's see what I can do that there. Okay, this is a differential equation. It's kind of complicated. It will grind away in version 14.3, and it probably isn't going to work. But oh, it just came back unevaluated. Version 15, this equation will get solved. And it's getting solved by a model that we trained that specifically solves differential equations. And it's a transformer net that looks at these differential equations, and not only is it able to solve new equations, it's not a large fraction of equations. So I mean, to be realistic, it's when we look at kind of books of tables and things, we can solve 100% of those with the methods that we already have. Right now, we're only looking at 0.003% of test equations tested on the sort of distribution of equations that are used in things like Wolfram Alpha, that we can make improvements to. Coming soon, there's a lot more along these lines where that's going to be more dramatic. But let me show you another thing. This is an equation where we have a solution in version 14.3, and it might take a while to grind through it, but it's kind of a mess. And in version 15, if it finally gets the solution in 14.3, I don't know if it will. In 15.0, we have the same equation. It might take a while here also, but okay, it's grinding, and both of them are grinding. Let's see what they produce. Okay, so version 15 finally produced this very nice result with the tan of an arc secant. Version 14.3 produced this big mess here, which perhaps could be simplified to that form, maybe not. I think full simplify can barely manage that. Okay, so it's just an example of a way in which we're using sort of the latest technology to inform even sort of core functionality within the system. But it relies on all of the frameworks and all of the training data and so on that we have to be able to do that. Okay, differential equations. Let's talk about PDEs a bit. Curvilinear coordinates for PDEs. So this is Laplacian in polar coordinates. That's something we've had for a while. But we are now extending support for coordinate systems to our things like our PDE components. So this is a Laplacian PDE term that is represented in polar coordinates. And we can now insert that into a whole differential equation and solve the equation in polar coordinates. Okay, so that's giving us this solution all the way in polar coordinates. So we're just working all the way in polar coordinates. We can do that for a sort of more, we could, for example, have a fluid flow PDE component. There it is, again, in polar coordinates with it's, you know, any, let's see, that's spherical coordinates. All these things now we can just solve PDEs in any coordinate system. Here's perhaps some more exotic ones, spheroidal coordinates, all kinds of weird functions showing up, complicated expressions now being generated there. So for example, if we just say, let's compute an solve for a Laplacian PDE term here, solve the eigenvalues of the Laplacian operator here in polar coordinates, this is what we'll have. And we get, and now to plot that, we can use a revolution plot to plot those functions which are now defined in polar coordinates. So now PDEs, you can work in polar coordinates. Okay, more in PDEs, derived quantities in PDEs. If you're doing solid mechanics, for example, you might define some variables, some parameters. You might define the displacement of you're computing the displacement of that little object there with respect to with certain forces. We've got a solid fixed boundary condition, with a load and so on. You're computing all those things and getting that result. But now we want to know, okay, we got that, but now tell us what's the consequence of that. We've got this deformation of the object. We want to work out the strain strain on that object. So this is a now solid mechanics strain, which derives the strain from the variables and the parameters and the displacement. Okay, so, and we've got, I think, equivalence strain is another strain that we can get here. And so now we can make a vector displacement plot of the original displacement together with this equivalent strain. So we're able to see the places where there is strain on this stretched object, a convenient thing to be able to do. What's this? This is for a different, okay, this is looking at the equivalent strain in a particular case with a particular Young's modulus and so on. Same kinds of things. We're introducing magnetic flux density, magnetic field intensity, lots of things that kind of deliver sort of convenient for kind of physical modeling in our framework. Okay. More on engineering, systems engineering models. Here's a model of a motor. We could open it up. We can see more detail here. It's a motor. Okay, if we do a plot, we solve we actually run a simulation of that motor. We'll get a plot. It's crunching away. It's using our system modeler technology stack, and it'll give us the turning of that motor as a function of probably time there. Okay, what if you want to not go through all that grinding and just make a machine learning model of this motor? Well, you can train a surrogate model. So it'll make simulations, it'll run multiple simulations and with all sorts of different parameters to train a surrogate model that approximates this actual motor model. And so it'll do a bunch of simulations here. It'll process the training data. Oops, what did I just do here? Oh, I must have interrupted it in some horrible way. Did I do? Okay, it finally came back with a system model surrogate and produced some weird messages here. Okay, so here's this thing. This is a machine learning model that is a surrogate for this systems engineering model. So for example, here I can say, go ahead and plot for the surrogate model that same curve. And so we see it looks the same here. But that ran much faster because it didn't have to actually solve the differential equations to compute what happens in the system. Instead, it just used the surrogate neural net system. And if we wanted to, we can actually see the neural net that got generated for this surrogate model. It'll be some complicated neural net here that is the underlying neural net surrogate model for this model that we were able to simulate here. Okay, let's go on. Next thing I want to talk about is about reinforcement learning for control systems. I mean, this reinforcement learning and control systems, very close. They've been separate branches, but optimal control, well, feedback, control, and reinforcement learning, very much the same thing. And this is all about sort of optimal control, but also about reinforcement learning. Okay, so we're dealing with a method called Q-learning, and the idea is to constantly try and learn a Q function that specifies the quality of response associated with a given control action when the system is in a certain state, and then take that learned Q function and derive a controller from the system for it. So it's a bit technical, but we're introducing a function called LQ regulator gain, LQ regulator train, that will train will train things using this Q-learning method. So this is a system that just takes inputs x, u, and k and gives that value. Let's train an LQ regulator. So this is a systems model of controller data. It's a linear quadratic regulator training. And we could say, let's show the state response of that regulator we're showing that state response. If we wanted to, we can actually see what's inside that linear quadratic regulator. There it is. It's a quadratic function like that. Okay, let's do something that's a bit like what we did before with motors. So let's take this in. This is a Modelica model. This is some kind of, I don't know what this is. This is some kind of object, some motor. And now we can, okay, this is getting wild and complicated. We are going to actually make a, we have, what on earth is this? This is, okay, we have a model for the device. We can actually run that. This is a piece of C code that is symbolically represented in Wolfram language as a foreign function. We can now train a regulator relative to this piece of code. I'm not sure why we're not just doing it directly from this model here, But in any case, I guess we can do this from any kind of external device. So we could actually have a physical device that we're training this from. So we have this, and now we can say, let's compare, let's look at the state response for this motor with this Q-learning method, its error in position, its error in angular velocity. Okay. More to talk about. Hopefully I'm getting near the end here. Let's talk about, we've added a bunch of new formats, various things about Markdown, various kinds of XML formats, importing as trees, things like that. Another kind of systems level thing is WebSockets. So this is a WebSocket now. That's a socket object. We're connected to the Echo socket here, that generic test socket. And we can go ahead and on that socket, we can read 32 bytes from that socket. We can then connect to that socket. And what is this? This is what on earth is this? This is a socket. Oh yeah, this is for reading from an LLM. So this is for real-time reading from an LLM. And that's what, in fact, we use in the modern chat notebook mechanism to stream data back from the LLM is a WebSocket. And the underlying infrastructure has been made available at a symbolic level in Wolfram language now in version 15. Okay, external programs. We've got, we have this, you type a greater than sign, you see all these different choices of different kinds of languages that you can use, that you can just type code in. I don't know most of these languages, so I'm kind of guessing you can type something like that. Does that work? I think it should work. Okay, it finally came back as 13. Now, what's interesting here is it's all the technology that we have for, this is now a session menu, because each one of these external evaluates, we can deal with different sessions with different dependencies. It's a big, horrible mess, but we can encapsulate that horrible mess into something which is symbolic and easy to use. So we could say, use a new Python session. We can configure that for the cell, use an existing running session, et cetera, et cetera, et cetera. We can also format code, external language code, and so on. By the way, you know, if Python was like Wolfram language, you probably wouldn't need multiple sessions, but it has all kinds of different libraries and dependencies, and one thing you need might need one library, another thing might need another library. The great thing now is you can just package it all up. So this is starting an external session that uses the emoji library as a dependency, and now we can operate with that library, and we could say, let's see, do I have this? I think I don't have this as something that I can type in, but I could say something like, I can import from that library, which is now available in this session. Actually, this session here I should look at, and I can do things where I'm just, you know, have a fully encapsulated piece of Python code. I mean, now we can fully encapsulate any C-connected language with foreign function interface. We can encapsulate Java, we can encapsulate Python, R, etc. All these things are things that can now be implementation languages for things which are ultimately Wolfram language functions. Okay, all right, let's talk about GPUs. Something new, we've added a bunch of GPU rearrangement functions. Flatten works directly on GPUs. We've also added the possibility of using external evaluate with CUDA. I don't know whether that's an option here. Let's see. No, it isn't yet. But you can go ahead and make a CUDA function. I'm afraid this is not going to work on my computer right now because I don't have CUDA set up on it. But you can take raw CUDA code, and this becomes a CUDA function that will just run in your GPU. But the CUDA function is available symbolically in the Wolfram language, just like it's a piece of built-in Wolfram language code. And okay, all this stuff connects in to let me just show you an example here. It connects into the Wolfram language compiler, so you can have external evaluate of library functions with CUDA and so on. All this stuff fits together. Okay, one more topic. Compute services, something that we introduced in last year. This is a way of, so we can just take, I'm going to do this, but then I'm going to kill this job because I don't really want to run it. I can just submit this whole pile of stuff, and I'm saying remote machine class, new for version 15, you can use GPUs. So this is now going to package up this whole machine learning training thing. It's going to turn it into a remote batch object. It's going to, and so now it's running, it's going to run on these machines. It's going to run on a big GPU, and I want to kill this. So let me go to my account here, and let's see. I think I can just go ahead, and there's my list of jobs, and I'm going to go pick this one here, and I'm just going to say terminate this job. Boom, it's gone. Bye-bye. Okay, but what's really convenient, I mean, I use this all the time. I have a couple hundred cores of my own, but when I want to just, fire and forget, just run this computation, it'll just, I just use remote batch submit. It'll send the results back to my email. It'll give me a symbolic thing that I put into any Wolfram language notebook, and that allows me to get the results from that computation. So it'll just run anytime I want and give me the results. I showed here, this is what an email looks like that comes back from that process. It'll tell me it's succeeded, and I can go and copy that remote batch job object to get the actual data that it generated. Okay, a little bit more here. Another thing is I talked about LLM functions. This is, we can now use our whole computation augmented generation stack, the same kinds of things that Wolfram Agent 1 uses. We can now use that programmatically within Wolfram language. And well, there's more, there's yet more, there's always more, but those are some of the highlights. Here's the Pfaffian, that's a thing we have, and new things like discrete Hilbert transforms, another new thing. We have changes to, we have Bezier surfaces. This has been something we've had B-splines for a long time. This is now a way to, that's something different. That's some face lists, but the planar with Bezier surfaces, this is something that's part of our 3D geometry. We can take that Bezier surface and we can do computational geometry on it. This is important for kind of computer-aided design kinds of purposes and so on. Other things in chemistry, we've got finding molecular substructure cases. We've got this pattern in a molecule. We can find all instances of that substructure in the molecule. Now we can go ahead and plot where those substructures occur in the molecule. All right, well, that's pretty much it, guys. Let me show you one more thing. I felt like as I was writing about this, I felt like we should shoot for the moon at the end. Well, we've had for a long time in geographics, we've had the ability to show where's the night hemisphere of things. And and we can do that in now in version 15, we can do that for other planets. Convenient if you're going there, I guess. And I thought, oh, I was just writing this yesterday, and I thought, I'm just going to do this for the moon. And it's like, wait a minute, what's going on? Where's the terminator, the day-night terminator on the moon? And is there a bug? What's going wrong? Well, needless to say, I then thought, look up moon phase. Yesterday it was 0.01, I think, but now it's 0.05. It's a new moon right now. Of course, if we go, we can, this is computational, so we can just say, find the night hemisphere for today plus 1 week. And we're using an orthographic projection because then we get to see the moon like we see it in the sky rather than flattened out like we would on a map. Okay, there it is. A week from now, we indeed have a quarter moon. Everything works fine. So we can successfully shoot for the moon here. All right, so that's the story. That's a bit of a look through version 15. It's I think it's very impressive. We've been working on many of the things in here for many years. We're now delivering this whole package of functionality, plugging into AI, being able to use AI from within a Wolfram environment, being able to use the Wolfram environment from within AI environments. It's welcome to our AI users. I'm sure this presentation will get ingested by AIs as well, and hope you learn from it, humans and AIs, and are able to make use of all of the technology that we've made all these years. So thanks for joining me. Download your version 15, use your version 15, have your AI use your version 15, use AI from within version 15, and discover and invent lots of great things with version 15. I've been able to use it for a little while now, and it's been really cool, and I've been able to advance all sorts of projects of mine using the new functionality of version 15, and I hope you guys will be able to do that too. So thanks for joining me, and I do want to add that there'll be a series of webinars in much more detail about the kinds of things I've talked about, things that are new in 15, getting up to speed with those kinds of things, lots of things that you can really use every day in using Wolfram language for many different purposes. Thanks for joining me. Bye for now.